Okay, you should grab out your notes packet. Today, you don't necessarily need the highlighters. You can use them if you wish. We're doing some word problems today, so if you're a person that highlights to kind of keep track of things, that'll be good. You will need a calculator, though. We are in our last section of notes. Oh, come on, scroll faster, iPad. There we go. That was better. Which is on our final page. So in section 8.5, we are talking about applications of proportions, because proportions get used in a number of different places in the real world if, well, you let them. One of the things that proportions can get used for, and we're going to see kind of two different types of problems. One use for them is working with scale problems. Things like maps, where they tell you 1 inch equals 100 miles, where you've got this scale factor essentially given to you that tells you how two different items that are meant to be representing one another, how a model that's supposed to represent a real thing, how the sizes relate. Another option that often gets talked about in math classes more than anything, but has some nice applications, is working with shadows, specifically in situations where there is a shadow being made by some light source that is particularly far away, and it helps us to measure things in an easier way. So, we're going to solve the following. We are going to round to the nearest hundredth if necessary. First problem says a man who is 6 feet tall casts a shadow that is 8 feet long. At the same time, a tree casts a shadow 22 feet long. How tall is the tree? So in situations where, like, measuring the height of the tree would be a challenge, that's where these shadow problems have their best advantage, is it allows you to measure things that would be hard to measure by just measuring other items that are easier to measure. It's easier to measure a shadow on the ground than it is to measure a tree. And it works out that they create a proportion with their shadows because of the fact that they are close to one another and their light source is the same. Their light source, assuming being the sun. Okay, so to do these problems, I always just kind of make myself a little picture. So I got a little dude, a stick figure. He is 6 feet tall. He is casting a shadow. Now, remember, when you make shadows, you make them on the ground. So he's got this shadow here on the ground that is 8 feet long. Now, we've also got this tree. My tree is clearly purple. And it's a pine tree, and it's kind of weird pine tree, but that's okay. And it is making a shadow on the ground. Its shadow is 22 feet long. We don't know its height. That's what we're trying to solve for. Now, because of the fact that they are close to one another and that light source being the sun, what ends up happening with these problems is we end up getting this triangle popping up and this triangle popping up that are similar to one another. They're similar because we assume both trees and people stand straight up, and this angle where they hit the ground will be the same. So by angle similarity, they will be similar triangles. Now, as a result, we can set up a proportion. We need to match up corresponding things. Corresponding sides. Shadows go with shadows. Heights of the object go with the height of the object. So, my proportion. I like to start with the x, so the height of the tree goes with the height of the man, is equal to tree's height and shadow length of tree are in the same triangle over the shadow length of the man. And we cross multiply to solve. 8 times x is 8x. 6 times 22 is 132. And we divide by 8. We get x equals 16.5. Now, in a word problem, you should answer in words. 16.5 feet is the height of the tree. I'm not saying you have to write a sentence, but you should put units on, is what I mean. When I give you a word problem, you should answer in words. Similar problem. A girl that is 140 centimeters tall stands 360 centimeters from a lamppost at night. Her shadow from the light is 90 centimeters long. How high is the lamppost? So, similar, but slightly different in this problem. Because this problem says, okay, I've got this girl standing here. She's 140 centimeters tall. And she is standing 360 centimeters from a lamppost. Okay, here's my lamppost. Her shadow from the light, now assuming, of course, the lamppost is lit up and it is what is creating the shadow. So we're getting this shadow coming down, creating, here is her shadow. It is 360. Nope, sorry, it is 90 centimeters long. Look at the right thing. Yes, I am well aware that my 90 centimeter looks significantly longer than my 360 centimeters. That's okay. How high is the lamppost? So, this is the other kind of setup. When it comes to the shadow problem, sometimes you'll get two separate triangles, like problem 1. Other times, the two triangles will be overlapping. The two triangles overlap when the source of light is one of the things that you're looking at in the problem, that you're getting measurements from. It's about the only time that you're not going to be having the sun as the major light source, because as the light source gets closer to the items, the angles start to change a little bit as you're working with them. So you really kind of want light sources that are far away to work with shadows. Now, we have our overlapping triangles. So we can recognize our corresponding parts. Now, I wish I had made my picture a little bit smaller, and I have the advantage of being able to shrink it a tiny bit. Because now when I'm matching up corresponding pieces, the height of the person and the height of the lamppost go together. That part's easy. But I also then need to work with the shadow of the person and then the shadow that goes all the way to the lamppost. So the shadow all the way across. So sometimes I'm still going to have to do some adding of things together to get those lengths. I need this length. 90 plus 360 is 450. And then I make my proportion. X over 140 equal to, so X came from the big triangle, which means 450 goes on top, over 90. Y'all know how to solve. I'm just going to straight up tell you, it is 700, and we're measuring in centimeters. Now, the other type of problem that you're going to see works with these scale problems, where they tell you the relationship between the lengths of items. So, problem 3, a model plane has a scale of 5 inches to 2 yards. If the model plane is 25 inches tall, then how tall is the real plane? Now, you have to make sure you're matching up things that work together, like height of model, height of plane. Those go together. Scale of model comes in 2 different numbers. So, when it's a scale problem, the scale itself, in this case, 5 inches to 2 yards, that can become one of your fractions. 5. Now, one of the things I do in these ones is for my initial proportion, I just write in what is my units, because that helps me with the other side. The other side has to work with units in corresponding places. Otherwise, it's not really gonna work. So, on the other side, the reason the measurements have to come in those corresponding units has to do with what goes on top and what goes on bottom. If the model plane has a scale of 5 inches to 2 yards, that means that the 5 inches is coming from the model and the 2 yards is coming from the real item. In my other fraction, I have to make sure model goes on top, real goes on bottom then, because it has to come from the same item. I'm given the model plane to be 25 inches tall. And you can kind of use the fact that the top is both inches to help you recognize where to put that. How tall is the real plane? X, and that's going to be in yards then. And then, as always, you cross multiply to solve. And you are going to find that the real plane, you guys know how to solve. You will get X is equal to 10 yards. So in the scale problems, you don't necessarily need the picture as much. Okay, 2 more problems. On afternoon, I have a feeling that's supposed to say one afternoon. A yardstick cast a shadow that is 2 feet long. The shadow of a nearby building at the same time was 16 feet long. How tall is the building? Yardstick, for some reason standing straight up. Don't ask me why. Cast a 2-foot shadow. Building nearby. Casting a 16-foot shadow. How tall is the building? Did you notice they didn't actually give you the length of the yardstick? Because you should know that length. How long is a yardstick? I hope you said 1 yard. Now again, because of the light source coming down from the sun, we end up with these similar triangles because, again, we assume that things stand straight up and therefore, and the sun hits them at the same angle. So I match up my corresponding parts, shadow with shadow, height of item with height of item. I like to start with x. X over 1 equals, since I started with x, which was from the building, I need the building shadow over the yardstick shadow. Cross multiply to solve, and I will find that x is equal to 8. Now, much like what we were talking about before, we've got mixed units in this problem. There's yards and then there's feet. Proportions are one of the few times you can work with mixed units, provided that these things have the same unit and these things have the same unit. Okay, or technically you could have the top and the bottom of the fraction with the same unit. As long as either the things both on the top and both on the bottom or in each individual fraction match units, you're good. Since the 2 and the 16 are both feet, this is the situation where those two match. That means this one has to both be in the same unit, in this case yards. Final problem. A free fall ride casts a shadow that is 80 feet long. Free fall ride, we got that. We got the people strapped into the thingamabob. Yeah, beautiful. Free fall ride. No, we don't know how long it is. It casts a shadow that is 80 feet long. A person standing nearby. Person. 5 foot 6 inches tall. Casts a 36-inch long shadow. How tall in feet is the free fall ride? Now, when I talk about us working with mixed units, one of the things we have to be picky about is the mixed units are not in the same measurement. So that 5 foot 6 inches is not going to work for us. That can't be a thing. Furthermore, when we make our proportion, as I mentioned earlier, either you have to have the situation where both of the top measurements have the same unit and the bottoms have the same unit, or each fraction has the same unit. If I look at this picture right now, my shadows generally correspond and my height of my items correspond. That's what I'm looking for, by the way. My shadows do not correspond currently. So if I go to make my fractions and I'm just going to start with the numbers this time. I'm going to have my 80 over my 36. That's in inches. That's in feet. Since those are not the same unit, that means this measurement needs to be in feet and this measurement here needs to be in inches. So 80 is in the same triangle because remember our light from the sun coming down creates this triangle. It's in the same triangle as the X, so I can put the X on top, and measuring the free fall ride in feet makes sense. But that means I must measure the person not in feet, but in inches to make this work. So I need to convert this. How many inches are in a foot? Please say 12. So 5 foot 6 inches is 5 feet getting multiplied by 12 inches to convert that part to inches, plus the additional 6 inches. 5 times 12 is 60 plus 6 means this is 66 inches. That's what has to go in our proportion. If you have those units like 5 foot 6 inches, you have to convert them to either feet or to inches. Which one you convert them to depends upon your fraction, depends upon your proportions, because you need, again, either these have to match units or these have to match units. Then, just as before, we cross multiply to solve, and we end up with getting x being equal to 146.67 feet.